So when you are looking at an oxidation reduction reaction, the electrons are transferred from one reactant to the other. The simplest form of these reactions are like our single replacement reactions that we talked about in Honors Chem. They can be a lot more complex than that, but that's the simplest version of it that you might recognize here. When you have a reaction, elements can lose electrons, or species in a compound can lose electrons, they can gain electrons, but in order for it to be a redox reaction, you have to have both. So you have to have something that loses electrons and something that gains electrons. We will come back to this, just like a lot of the other stuff in this chapter, second semester when we do what's called electrochemistry, because when you do have a transfer of electrons like that, the reaction can actually generate electricity, like in a battery, for example. So we'll learn how to balance these later on, and we'll come back and talk a lot more about these in the spring. But for now, we're just going to do kind of a general, how to identify it, and how to look at oxidation states. So oxidation is known as a loss of electrons. Reduction is a gain of electrons. And then an oxidizing agent is the substance that's reduced. And then the reducing agent is the substance that's oxidized, because a reducing agent is causing the other one to be reduced. The oxidizing agent is causing the other one to be oxidized. So a mnemonic you can use to remember this is Leo says GER. That's the easiest one, I think. Oil rig is another version of that. Leo stands for a loss of electrons is oxidation. GER is a gain of electrons is reduction. The other version is oxidation involves loss, a reduction involves gain. So whichever one of those makes more sense, you can use that to remember. So what we're going to look at today is how to identify the oxidation state or the oxidation number in a compound or an element or an ion. So what this does is it helps us keep track of the electrons. So when you have even a neutral compound, the electrons don't always stay with the original owner of the electrons, if you want to think of it that way. So the electrons get pulled to the most electronegative ion or the most electronegative atom. So we've talked about electronegativity in honors. We'll come back to that in a couple of chapters. You don't have to be able to figure out where they get pulled. The way you could do that is by identifying these oxidation states. So that's why sometimes the values of the oxidation states of an atom or ion is not what you normally would have thought it was based on what we know about the patterns of ions on the periodic table. So shared electrons are assigned to atoms that are attracted most strongly, and again, it has to do with electronegativity, and we'll come back and talk about that later. And then the oxidation state is given to each of the atoms in a compound based on those assignments. So to start with this, there's a set of rules. So this set of rules, you don't really have to memorize it, because by the time you do a handful of these, you'll remember what these oxidation states are. So I'm going to give you an example of each one of these as we go through. So this list, if you didn't write it down when you were doing the notes, this practice sheet that's in the back of your packet, this list at the top is this list that we're going to go through. So you don't have to write all these down, but if you flip to the back of your packet, that's where these rules are. Okay, so this is what this looks like. So oxidation number of a free element is always 0. So what that means, if I have just like sodium or even like a polyatomic element, the value is going to be 0. So when we write the oxidation states, we write them over the top of the elements. So when it asks for oxidation states, you're going to use those numbers that you write over the top. So sodium would be 0, Cl2 would be 0, any neutral element by itself would be 0. If you have an ion, so let's say Na plus or Cl minus, the oxidation state is whatever the charge on the ion is. So if it's a monatomic ion, a single element with a charge, then it's whatever the charge is. So Na plus would have an oxidation state of +1, Cl minus would have an oxidation state of -1. Normally hydrogen is +1. So like if I have hydrogen in this compound, unless it's combined with an element that's less electronegative than it is, which usually means it would be combined with a metal. So something like this. So in this case, H would be a +1. And here, if H is combined with a metal, that's what we mean by negative. So the reason we're using these rules is when you have a compound, you're going to identify the elements that you have rules for, assign those oxidation numbers first, then you're going to use those to figure out the rest of them. Oxygen is another one that usually has a rule. So oxygen in most compounds is -2 unless it's a peroxide. So a peroxide, that's a polyatomic ion. So it's O2 with a charge of -2. So the way you would be able to tell is if you look at this compound, if this was just hydrogen and regular oxygen, the formula would be H2O. But because it's that H2O2 compound, another common one you'll see is K2O2 as a peroxide. So that's when oxygen is not a -2. So like in this case up here, it would be a -2. But down here, if it's this peroxide, then it's a -1. So usually oxygen is -2, you just have to watch for those peroxides. If it's a group 1 element, it's a +1. So now we're kind of getting back into these rules that we know from before. Group 1s are +1s, group 2s are +2s. Group 7 is usually a -1, but if it's a group of more than 2 elements, then a lot of times the group 17, they don't have their normal charge, and we'll look at some examples of those. And then the last 2 rules have to do with how we figure out the rest of the elements. So the sum of the oxidation numbers in all of the atoms in a neutral compound is 0. So what we mean by that, like if I have, say I have Al2O3. Okay, so I know from my rules that oxygen is a -2. -2. Okay, so that means when I total the oxidation states for all of those charges, this particular compound is neutral, so that means everything has to equal 0. So the way that works is if I know oxygen's a -2 and there's 3 of them, that's contributing a -3 charge to that whole species. Okay, aluminum, if there's 2 aluminum over on this side, what oxidation state would aluminum have to be to balance that whole charge out to 0? +3, okay? So then 3 times 2 is +6, so then that equals 0 at the bottom. The big thing to remember when you're doing the calculations though, it's always going to ask for the oxidation state. So you're always going to report those numbers at the top, not that stuff at the bottom that you're using to calculate. If it's a polyatomic ion, then the sum of the oxidation states equals the charge on the ion. So if I have, let's see, PO4 -3. Okay, so if that's my substance that I'm figuring out oxidation states for, oxygen I know is a -2. So this one, instead of equaling 0, because it has a charge, it has to equal whatever the charge is. So if oxygen's a -2 and there's 4 of them, that's a -8. There's 1 phosphorus, so what does phosphorus have to be in order to equal -3? +5, okay? And then those are your oxidation numbers. Okay, questions on how to do those. And these, once you do some practice with these, they'll get a lot easier because you'll remember that hydrogen's a -1 or a +1, oxygen's a -2, and then pretty much everything else falls in line. All right, so let's real quick do the examples that are in your notes. Okay, those are just the ones we talked about. Just so we can reinforce this a little bit. Okay, so Cl2, neutral element, what would its oxidation state be? 0. Okay, and I'm going to continue writing them at the top so we can get it. What about Na+? Good, +1. Kf, I'm going to use my rules. So since there's only 2 elements here, I can assign F its normal charge of -1. They're going to equal 0, so K has to be +1. CO2. O gets a charge of -2. Acetone is 0. So carbon would be +4. And again, oxidation numbers, or oxidation states, those are the ones at the top. SO4 -2. This one's going to total -2. Oxygens are -2. There's 8. So that means for this to balance to 0, or I'm sorry, to -2, this sulfur has to be a +6. Okay, so you'll see a lot of those nonmetals having charges that we're not familiar with. So we know that when we're putting sulfur in a compound, it's usually a -2. But when you have stuff that has charges or you have multiple elements in a substance, you'll see that it doesn't always have the charge that we're. Okay, last one on here, K2O2. This one is the peroxide example. So oxygen is not a -2, it's going to be a -1. So that's a -2, has to equal 0. So what's potassium going to be in this case?
2.
Yeah, okay, so at the bottom it has to be +2, so what does oxidation state going to be? +1, okay? Okay, let's do one other one just so you can see what happens if you have more than 2 elements. Okay, when you have more than 2 elements, you're going to work from the outside to the middle. So on the outside, usually there's going to be at least 1 that you know of, usually 2 that you can predict. So in this case, we would assign that -2 to oxygen and our +1 to hydrogen. So 4 times 2 is -8. This is neutral, so it's going to be 0. Okay, sorry guys. So this should have been +1. This should have been +3. Yeah, Jefferson's just That's 5. So phosphorus in that case is a +1.